optimization, what about the other courses? How did you find them? Devyani?
Ma'am, I thought they were similar.
Similar, okay. Okay, fine. So let's begin the next part of this course. Okay, so where we left off, we were we started off with linear programs, and we were looking at We looked at some examples. So linear program was something of this form, right? You had this min of a linear term, and you had some linear constraints. Okay, and we saw a geometric way to solve it, and I think this is something that I think most of you have got it. And even in the midterm, I saw that people have done a good job on this. Okay, and so we looked at what is called the standard form of a linear program, and then there were some ways to convert other programs, other linear programs into the standard form. And then we also had this notion of basic solutions, right? Okay, so we had, it was basically to see, I mean, not about the optimality, but about the feasible point, and where you say that, if you have an m cross n system, you can, take out some of the parts, okay, some of the vectors which are linearly independent, you represent them with this matrix B, and you have some non-basic columns as well. So accordingly, the variables get grouped into two, the basic variables and the non-basic variables. Okay, so this kind of a division, if you can have, and that's what is called a basic solution which for which you can have a split in this way. Okay, and then we saw basic feasible solutions. Okay, and then we saw some examples of how to construct these kind of solutions, and then we saw this fundamental theorem which said that if an LP is feasible, then there is going to be a basic feasible solution, and if there's an optimal feasible solution, there's an optimal basic feasible solution. Okay, this we saw, and then finally we saw this notion of extreme points. Okay, so where we said that an extreme point is a point which you cannot represent as a convex combination of other points. Okay, and it turned out that extreme points and basic feasible solutions, they correspond to each other. They are actually one and the same. Okay, so in an intuitive sense, these extreme points are indeed the vertices of the feasible region. Okay, and in order to find the optimal solution, one way is just you find out all the vertices, that those are the extreme points, or in other words, those are the basic feasible solutions, and then you find which of them gives you the best. So in fact, many of you have used this approach for the question, so that's a good thing. Okay, so this is kind of where we stopped. Okay, so yeah, so today I just want to continue this discussion a little more. In two dimensions, or in very small dimensions, this approach of finding all the extreme points or the vertices, that is fine. Okay, so you can manually try and see the point where some group of them meet, like these two lines where they meet. So things like that you can do, and it's not very hard. But as you have like more dimensions, then this is not very straightforward to do this. Okay, and so that's why it kind of motivates the need for other sort of algorithms here, like a formal algorithm to solve these kind of problems. Okay, and that is the simplex algorithm. So we're going to look at the simplex algorithm. So one thing I wanted to just remind you. So for these basic feasible solutions, so an additional thing that helps is a point that will come up, will be useful later, is that so this B is a basis for Rm. Okay, so now any of these non-basic column vectors you take, that also you can represent as a linear combination of these basis vectors. Okay, so that is a fact that I would like you to just have at the back of your mind, because that will play a role later. Okay, so to just get an intuitive sense of what the simplex algorithm is. So it's exactly going to try to find an optimal basic feasible solution. But the way to do that won't be by computing all of them. So it's going to be an iterative scheme where you start off from one vertex and you progressively move to another vertex which you think will be better. Okay, so there are linear programs in which the number of vertices are like very huge. They're of the order exponential. So it's not feasible thing to write all the vertices, compute all the vertices, and do the step. Okay, so that becomes hard. So you can do something a little smarter, where you don't have to visit all of them. You just intelligently make a choice of which vertices you want to it's like you shortlist some vertices. Okay, I just want to give one example. Okay, here this is a linear program in which this is the feasible region. Okay, and I've drawn this here so you can check that this is indeed the feasible region. So this part is the feasible region, and these are the four vertices. Okay, so ideally, so if you write it in standard form, I mean, where you introduce some slack variables, this is going to be something like this, right? X1 plus X2 plus X3 equals 1, and minus X1 plus 2X2 plus X4 equals 1. Okay, so additionally you introduce two more variables. So now it becomes like there are four variables. Okay, and there are four columns in the system. And if you wanted to choose a basic solution, okay, what you would do is you'd pick two of them, which had to be linearly independent. So the possibilities are, there are four choose two possibilities. I mean, all possibilities. Okay, so of which some of them will give you basic feasible solutions, and some of them won't. Okay, so here it turns out there are four of them which are basic feasible, and I've just written these four vertices here. Okay, so now if you look at the corresponding basic feasible solutions, okay, so let's take this one. So this was I've just written this matrix here. Okay, so this is the original matrix, and this is the right hand side. So this 1 1, that's what is written here. Okay, so now if I fix this as the basis, the last three, so what does it so what are the basic variables now? What does this correspond to? So if I fix this as the basic column vectors, what would be xb and what would be xn? Somebody? Okay, I hope I'm audible and I'm connected.
Yes, ma'am.
Okay. So can you just tell me what are the basic variables?
1 0 and 0 1, the columns would be the basic variables.
Yeah, these are the basic x3, x4. Yeah, so these are the basic vectors. So corresponding to these, so this corresponds to x1, this corresponds to x2, this is x3, and this corresponds to x4, right? So x3 and x4 are the basic variables, okay? And x1 and x2 are the non-basic variables. So they get set to 0. And x3 and x4 are set to satisfy this equation. So x3 plus 0x4 is 1, and 0x3 plus x4 is 1. Okay, so this x3 and x4 are set to satisfy this. And this is going to be giving you a unique solution. Okay, because this is, I mean, both these columns are linearly independent. Okay, so, so this actually corresponds to the point 0, 0. Okay. Now, if you look at, say, the point D, okay, so this is sort of an adjacent vertex, right? So the adjacent vertices here are B and D. So D is one of the adjacent vertices to C. So if you look at the corresponding basic feasible solution here, okay, so that is going to correspond to these two columns. Okay, so it turns out that if you solve these, like x2 plus x3, so if you fix these as the basic vectors, then what it means is that x1 and x4 are zeros. Okay, and so if you solve this system, x2 plus x3 is 1, and 2x2 is 1. So what you're going to get is x2 is half and the x1 is 0. So that's going to give you this vertex D. So now if you look at these two basic feasible solutions between 1 and 2, okay, so corresponding to C and D, if you look at the basic feasible solutions, you will notice that these two, so this column and this column, those were common, okay, and there was exactly one vector which was different. So instead of this vector, uh, for the vertex D, you have this vector. Okay, so there is one which is common and one which is different. Okay, and similarly, if you look at now, let's say if you look at B. Okay, so B is this one, so it's this point, so it's 1 0. Okay, so basically, if you take this as your basis, okay, so what you're going to get is right, so x1 plus x, okay, so this is for A, right? So yeah, for B, if you take, so, and let me just repeat, so if I'm looking at this point, okay, if I'm looking at this vertex, the basic feasible solution corresponds to first column and the last column. Okay, so x2 and x3 are 0 and x1 is 1. Okay, so now again, if you compare this and the one for C, right? So this one was common. So 0, 1 here, the last column, and this last column, that was common. That was a common basic vector. In this, for B, we had this first column, which served as a basic vector. Whereas for this one, there was the third column, right, x3. Okay, so if you notice, I mean, you can notice a similar thing with A. So suppose you look at A and you compare B and D. So there also you will notice that, exactly one of the basic vectors is going to be common between A and D. And there's one which is going to be different. Okay, similarly for A and B. So this is a feature of, these adjacent vertices or adjacent extreme points. So in general, if you have an, n cross n system, so between the adjacent basic feasible solutions, there will be a set of m minus 1. So let me just write this. So if you have a system of m cross n, okay, so A is in R n cross n, so the basis is always going to be of size n cross m, right? So m linearly independent vectors. So here, of course, we assume that m is less than n, okay? So you are going to have m linearly independent vectors from this set, okay? And what we are saying here is that if you take, two basic feasible solutions, there are going to be m minus 1, which will be common. So between, so suppose I have x and x tilde, okay? X and x tilde. So between these two, so these are basic feasible solutions. And between these, there'll be a corresponding vector, right? So b1 and say n1. And here this will correspond to some b2 and 2. Okay. So now if you look at b1 and b2, in these there'll be some m minus 1 common vectors. Okay. Between b1 and b2, and only one will differ. Okay, so what is going to happen is, you can view this, if you want to go from one vertex to the other, what you could do is you try to remove one of the basic vectors. So suppose you want to go from x tilde to x. So this b1 has m vectors, right? M of these basic solutions, so m vectors. So you can think of this process as identifying one of the vectors in b1 which has to, leave the system. And so then you have now a system of m minus 1 vectors. And in place of the one which went out, you try to bring in one of these other columns. Okay, so one of these other columns is going to enter. So that would give you b2. Okay, so that is a view of these adjacent extreme points, and that's what the simplex method is going to use. Okay, that it uses this fact extensively. Okay, so is this idea clear, like what we mean about going from one point to the other? Guys? Yes, no?
Yes, ma'am.
Yes. Okay. Yes, okay. So please be really interactive because these concepts are sometimes a bit hard to grasp from textbooks. Okay, because there's a lot of some finer ideas which come in but which don't get described. So I want you to be really attentive and ask if there are questions. Okay. um, all right. Okay, so now the idea in simplex methods. So these are some of the some of the sub components which come in the simplex method. So the overall procedure in the simplex method goes like this. Okay, so it's all about identifying the basic feasible solutions, as I said earlier, and you don't enumerate all of them. So instead, what you do is you start off with a basic feasible solution. Somehow you fix a basic feasible solution, and you somehow have some way to check if the current BFS is optimal or not. Okay, and if you find that it's optimal, then you stop. Okay, you've already reached. But if not, you try to find a way to go to the next BFS. Okay, so this idea that I told you, that there are common n-1 common vectors between two adjacent basic feasible solutions. So what you do is you now find a new basis to enter. Okay, and you find, so based on some criteria, okay, that will come to. So you identify which is the new basic vector which has to enter, and identify a new basic vector which has to leave the system. Okay, and you keep doing this. So now this is going to give you a new BFS. Okay, and then you see if this BFS is optimal. If yes, you stop, and again, if not, you try to move to another vertex. Okay, so something like this. So in this setup, maybe you start with C, and then maybe the next step you find that it's most beneficial to go to D, and so then you try to construct this vector D, and after that you see that you're not still optimal, then you try to go to A. So, okay, so that's the idea of the simplex. So progressively you try to reach the best. Okay, so now what we'll do is we'll try to look at each of these components. Okay, so let's okay, so that's going to be the flow of what we're going to do. Okay, so we'll start from this end. Okay, from the last step, because yeah, you will see later why. I mean, this seemed to be the most appealing way to do this. Okay, so let's just see that. Okay, so at this point, what we have is we have found some basic feasible solution. We know that it's not optimal, and we found some new basic vector to enter. Okay, and you want to find which basic vector leaves the system. Okay, so that's this step about. So you want to identify what is the best vector which should leave the system in order to give you your new basic feasible solution. Okay, so is the statement clear of this step?
Yes, ma'am.
Yes. Okay, so I want to hear from some of the others as well. Siddharth,
Yes, ma'am.
Ankit, yes. Okay. Okay. Yes. Okay. Good. Okay. So, so remember, now the current basic feasible solution is something like this. There is a B and there is an N. Okay, may not all be contiguous like this. It can be spread out in the matrix. Okay, but suppose you have like without loss of generality, you can assume that it comes together. Okay, if it doesn't, it's just about reorganizing some of the variables. Okay, some of the columns it just gets interchanged, but that's fine. Okay, so the basic current feasible solution you have is something like this. Now, one thing in simplex is that it always tries to maintain this basis as the identity. Okay, so you can have different types of bases. So far, all the examples we saw, we didn't have it as identity, but for simplicity, what it does is, if you make this identity, right, if the basis, you can transform it to identity, right? So the idea is you just multiply this whole system with B inverse. Okay, you left multiply it with B inverse. So that's going to give you I, and this is going to become B inverse N, and this is going to give you B inverse B. Okay, so the reason is just that if you have it in this form, So I, this is going to be a diagonal matrix of just 1, 1, 1. All these are going to be diagonal. So you can just read off the solution as B inverse B. So all these basic variables are going to take this value of B inverse B. And the non-basic variables take a value of 0. So that's the reason why it's just transformed into I. Okay, so Simplex always maintains that, you know, the basic the basis that you get is going to be I. Okay, now you might not have started off with I, but you know, it ultimately tries to transform it this way. And in order to do this, you don't actually have to compute the B inverse every time. So you could do this with some row operations. Okay, so I think just a recap. So if you have a matrix A, and if you want to take its inverse, so one way that is used, I mean, it's to use this Gauss elimination, where you write A and you write I side by side. Okay, and then you do some row operations on both these, and so that you transform this to I. And the same row operations, if you do for I as well, you know, when you start off, if you do the same operations here, you're going to get A inverse. Okay, so that's going to be the whole overall idea. Okay, so you can just achieve this with row operations. Okay, so yeah, I hope this point is known to you all, or you know, I hope you remember this. Okay. Yes. Okay. So let's just see the setup now again. So the basic feasible solution. So since Simplex assumes that it's always going to be I, so what is going to happen is at one step you're going to have this identity, okay, and if you write out this, the system. Okay, you're going to have an m cross n system, out of which, you know, m of them are going to be form the identity matrix, and the rest of them have some values. Okay, let's write it in this way. Okay, so this is m column vectors, and the remaining of them I'm just going to write it as, you know, y1 m plus 1. So the first row m plus 1 column, then y1 m plus 2, like that, and y1 p. Okay, so let's just just ignore these things. I will just explain things as it comes along. So n plus 1, n plus 2, and so on. So the pth one is written as y1p, and pth column. Okay, and then you have y1n up to y1n. And similarly for the second row, you have this representation, and this is going to be this whatever was you had as the small b. So instead of that, I'm just going to write it as y10, y20, and so on up to yn0. Okay, so this part is going to represent the b inverse n. Okay, so the non-basic vectors, the non-basic column vectors, and this part is the solution. So what this means is that, so this is written in a contiguous manner. So this corresponds to x1. This is going to correspond to x2. And so on up to xm. Okay, and all these variables, xm plus 1 and so on up to xn, those are 0. And x1 is equal to y10. Okay, x2 is equal to y20, and so on. Okay, so that's what this representation means. It's also referred to as a tableau. Okay, so we will see examples of this. I will illustrate this later. Okay, so now at this point, what we are saying is that one of these, this is a basic feasible solution that you have at this point. And you know that one of these is going to leave and one of this is going to enter. One of these non-basic variables, non-basic column vectors is going to enter. So what is going to happen is, if suppose the first column, so if you decided that this was the column vector that has to leave the basis, then, and suppose you assume that this is the one that's going to enter. Okay, we will see how you choose the one that's going to enter. But suppose you fix that this first column leaves the basis, and the second and the pth column is going to enter. Okay, so in place of this 100, you're going to have this as the new basic vector. Okay, and so because Simplex always maintains this as the identity, now what you have to do is the pth column, instead of this y1p, y2p, and so on up to ymp, you need to make it as 1000. Okay, because this is coming in place of the first column. Okay, now similarly, if this is the column, the second column is the one that you decide that it had to leave, and you were bringing in this pth column. So what would happen is the pth column, so this is going to leave, right? So this one is going to leave. So you had to, what you will need to do is you'll have to make this as 0, 1, 0, 0. This pth column vector has to be made 0, 1, 0, 0, 0. Okay, so in that manner. So if the qth column is going to leave, this pth vector needs to be transformed into this form, 0, 1, and so on, so that the qth entry, the qth row is going to be 0. Okay, so I hope this idea is clear. Okay, does it make sense?
Yes, ma'am.
Yes.
Yes. Okay. Okay, so that's what this step is going to be all about. So let's just see how you do this. So suppose you're given this pair, how would you do this, right? I mean, and that's just the row operations, right? So you want to make the qth, so the qth column is going to leave and the pth column here is going to enter. So you want to make this entry q. So the qth row of this tableau should be such that here in this position, so yqp comes somewhere here, and that you want to make it as a 1. Okay, and all these others you want to make it as a 0. So how do you do that?
The Gauss eliminate the row operations.
Row operations. So can you tell me specifically what are the row operations that you would do?
Divide all rows by divide the qth row by yqp.
Yes.
And then subtract like a ratio thing.
Yes, exactly. So that's exactly what this step is going to do. So row q is going to be row, you need to transform it to row, you need to divide it by the yqp. Okay, and all other rows, so you want to make all these values as 0. Okay, so what you will do is you will subtract out, right? So this one, the first row, what you're going to do is you will multiply the qth row. Okay, so yqp is there, so you need to subtract out some ratio, okay, from this yqp, and that ratio is just this. Okay, so yqp, so this is the entry, the corresponding entry in the qth column. Okay, sorry, the qth row. So this is the qth row here. Okay, and so this is the entry corresponding to the jth, sorry, what I think something I've messed up here. So yij, right? So for every other row, right? Yeah. Okay. So this part is particularly about the whole matrix, how this whole thing changes. So what you would do is you would take this ratio, right? Yip by yqp. So this entry divided by yqp, that you would take and you would multiply with this whole row. Okay. Okay. And then you would subtract that from this column. Right? I mean, sorry, from this row. So row, the first row is going to be changed into row 1 minus y1p by yqp times row q. Okay, so that is just what is written here. Okay, so yij is just yij minus yip by yqp into yqg. Okay, and the qth row is just going to be you just divided by yqp. So is this clear? I mean, this is just exactly the row operations which is written in a mathematical way. Okay, is this clear? Yeah.
And what if yqp is 0?
Yeah, so that the assumption is it's not going to happen, and you will see like it will not happen because of the way we are going to choose this pth vector. Okay, the pth column will be such that that will never happen. Okay, so we'll just come to that in a minute. Okay, so I hope this idea of this row operations, how you did this, is clear. Okay, so are there any questions on that?
Ma'am, but won't this row operation disturb the identity matrix in the B part?
In this part. So actually here in this identity, what's going to happen is all these things will be zeros, right? Right. So all of these parts are going to give you 0.
1, right?
Pardon?
One of them would be 1.
One of them would be 1 here.
Yes, ma'am.
So exactly the one that's going to leave, right? That column will get affected. So if you say this is the qth column that's going to leave, now what it's going to affect is only this column, right? Sorry. Yeah. So this in this column, yes, that will get affected, but that's anyway going to leave the system. So all other columns, it will not change because you're going to have zeros here.
Yes, ma'am, got it.
Got it? Okay. Yeah. So that's a good point. So yeah. So I hope this much is clear. So any questions? Any other questions on it? Okay, so I assume it's clear. So let's just see now how we are going to, so this, if you had fixed the row Q and the row P, column Q and the column P, the particular columns here, the two pairs of columns, if you had fixed, you know what to do, okay, to transform this into identity, okay. So now the question is, how do you fix this P? Okay, you fix the column Q, that is from a previous step, and how will you fix this P? So now in doing that, remember that these values, so you're going to do these row operations on this whole tableau that's written here, including these this part. So this is some operations that you did on the B part, on the right hand side of the feasible region, that AX equals B, and you had that, and this is going to be some operations that you did, and here again you're going to do these row operations even for this column as well. Okay, so now when you do this, you have to ensure that this is actually what is going to give you the values of the basic solutions. So these have to be greater than or equal to 0, because the feasible region is always, we assume that we're working in a standard form. So this has to be always maintained. So x has to be greater than or equal to 0. Okay, so now, so all of these elements, so the last column, that will give you, if you apply this, it's going to give you the same thing. yi0 is equal to yi0 minus yip by yqp times yq0. Okay, so yq0 is something here. Okay, so this has to be greater than or equal to 0. Or in other words, this ratio, right? If you just rearrange these terms, what you're going to have is yq0 by yqp has to be less than yi0 by yip for all these rows, and this has to be greater than or equal to 0. Okay, so this is just the values of the basic the basic solutions, and that has to be greater than 0, and so that's why you have this is going to be true.